In this video, I just want to explore with you the solutions that we get to the second order, linear, constant coefficient, homogeneous DE. We explored the three types and the three kinds of solutions we get, and I just want to go over what the behavior is, what these three kinds of functions look like, what they do. Alright, so remember the three possibilities, depending on how the algebraic equation in lambda comes out, are you could get two exponentials, you could get one exponential and then t times the same exponential, or you could get, and this was if you got complex numbers out of your quadratic formula, you could get an exponential times a trig function. So let's take each of these in turn. Let's first talk about if you have two exponentials. What does that look like? Let's first consider the case where there are two positive exponentials. Now, we of course know what an exponential looks like. Here's, for example, the graph of 3e to the 2t. And of course it grows exponentially. It grows very fast. Even when we draw it by hand in class, we usually don't draw it really as fast as it goes. We kind of draw it going up, but it really does take off and go very steeply, very quickly. So that's 3e to the 2t. Now that's one exponential, right? And of course ours in general has two different exponentials. So let me put in another one. Let's do, let's say a 1/3 t. Okay, so that also is an exponential. It doesn't grow quite as fast because it's 1/3 t as opposed to 2t. Right. So now if we add these two together, two of these together, so 3e to the 2t plus 8e to the 1/3 t. And this is the black one. And so you see it's, of course it's, well, because these were both positive in this example, this is bigger. But it grows pretty exponentially as well. It technically is not a single exponential function like the individual ones are, but it grows kind of the same way. It kind of follows the first one. It follows the bigger exponential. And that's going to be the conclusion. That's the lesson, which is that whichever of the two exponentials is the bigger one, in this case the 2t versus the 1/3 t, that one's going to dominate in the long term. And very quickly, the smaller one is going to matter less. I mean, it's an exponential. It's a positive exponential, so it's no slack. You see it's pretty big. It doesn't take very long for it to get big. But compared to the other one, it's going to be nothing. It's going to be negligible. So the larger of the two exponentials kind of dominates and controls the behavior. But yeah, the bigger one, it pretty much follows what would to us look like a typical exponential graph. Now let's start over and let's suppose we have two exponentials, but one is positive and one is a negative exponential. Okay, so there's our positive again, 3e to the 2t. And let's do negative e to the negative t. And so hopefully this isn't a surprise what a negative exponential looks like. Right, that's exponential decay. It very quickly dies off to 0. Okay. And if we now put them both together, here we are. So again, the positive one going up, the negative one going down, and we see that when you add them together, actually before time 0, in the negative t region, it follows the negative one, but then very quickly the positive one takes over, and the overall will follow the positive one. So again, at least going into the future, it's the bigger one that dominates. And in this case, if you have a positive and a negative one, the positive one is clearly going to dominate. Okay. One more restart on this case. Let's do two negatives. What happens if you have two negatives? So let's do the 8e to the minus t again. But now let's add in a y equals 2. Well, let's make it a bigger number. Let's make it like 15e to the, and let's make it negative 2t. All right, so there you go. That's what that one looks like, the green one. And I gave it a bigger coefficient, so it starts up higher, but very quickly it dives down lower and it gets to 0 faster than the first one because it's more negative. Now, when I put them both together, here we go. This is the orange one, and you can see that it comes down. Of course, it also exponentially decays. And what I hope you're seeing is that it's getting close to the pink one, which was the e to the minus t1. Now, that one was the bigger exponential technically, right? It's less negative, so that one was the bigger one. So once again, we see that when you add them together, the sum will follow the bigger one. The bigger one is really what dominates the behavior. I can zoom in a little bit more. Okay, it actually doesn't look too different, but I actually zoomed in quite a lot, and you do see the orange one following the red one, the e to the minus t1. The e to the minus 2t is just too small to matter when you add them together. Okay, so just to summarize, our conclusion when we have this kind of a function as a solution to this differential equation is we can think of it as behaving, at least in terms of positive t going forward in time, we think of it as behaving like the bigger of the two exponentials. Now, if the bigger one is positive, then that's going to be going up. If they're both negative, so that the bigger one is a negative exponential, then it will decay. All right. Okay, moving on to case 2. Case 2, this was the formula we get, and this came out when we solved the corresponding algebraic characteristic equation, we got 1 lambda, and we got it kind of twice because it factored as something squared. Then we only have 1 lambda, we only have 1 exponential, so our two functions that we put together are that exponential and then t times that exponential. Now, how does that behave? Well, just show you kind of all at once here. Here is an exponential. This is the red one going up this way, and I'm scaled out in my y-axis I'm zoomed out pretty far so that this is growing slower than it really is if I was on a true scale. But there you go. There's the exponential growth of an e to the 1/3 t. Now, the purple one is t times that. And as expected, maybe not at the beginning, but pretty quickly, this gets to be bigger. Because it's not only the exponential, but we're also multiplying by t itself. It's going to be bigger. And when we put them together, this is not a huge surprise. This is the black one, and we see that the black one, for the most part, is following the second one. It's following the one that had the t involved, because the t one is bigger, so it's going to dominate. The black one really is the purple one plus the red one, but the red one's just not as big, so the black one is going to be just kind of a little bit bigger than the blue one. And there's definitely a lot of space still here between these two, but I think if we zoomed out more and more and more and follow this up, 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 we would see them getting closer and closer, relatively speaking. Yeah. So, yeah, we're dominating by the second term, which is a little bit, it's like an exponential plus, right? It's, well, or I should say an exponential times. It's t times an exponential, so a little bit faster than a typical exponential. Okay. Okay, now going on to the third one. Now the third one, as you might guess, is going to be considerably different because we have these trig functions in there as well. So before I go to the graphs, I'm going to show you a little bit of a manipulation that can help us understand this a little better. Okay, here's our solution. Here's our function that we want to understand. And one thing I'm going to do is I can definitely factor out the e to the alpha t, the exponential part, because that's shared between the two. So I get this. So I get an exponential times, and then I have this kind of linear combination of a cosine and a sine of the same thing. Notice it's cosine and sine both of beta t. So here's what we're going to do. We're going to try to understand. We kind of know how this works. If this is a positive or a negative exponential, we know what this is bringing to the table. But let's try to understand what the trig part is doing. So let's just focus only on what's in parentheses just for a second. So this is actually going to be a slight aside that is sort of a purely trigonometry kind of idea here, and then we'll go back and apply it to our function. So let's just look at a times cosine of something plus b times sine of something. And again, those two things inside are the same. And let's see what we can do with this. Now here's the idea. We're going to draw a triangle whose sides are, whose the legs are A and B. It's a right triangle. So let's build a right triangle whose sides are based on these two coefficients. Now the hypotenuse by the Pythagorean theorem would be a squared plus b squared. And let's call this angle that we get that's opposite from the b and adjacent to the a, let's call that little delta. So notice that the tangent of delta would be b over a, right? SOHCAHTOA, opposite over adjacent. So in other words, so both delta and the hypotenuse I can get if I know a and b, because it's a right triangle. Well then, now a is the adjacent side to delta, right? So a is the hypotenuse times the cosine of delta. And b, by the same token, is the hypotenuse times the sine of delta. So I've written my a and b, which were just two arbitrary numbers at this point, in terms of it's this one number times a cosine and times a sine respectively. So I can turn my expression here into, now we got square root of a squared plus b squared, sine of delta, cosine of delta, and then the cosine of theta that we already had, plus square root of a squared plus b squared, sine of delta, sine of theta. Now they both have this square root of a squared plus b squared in common. I can factor that out. And what's left is a cosine times a cosine, two different things inside, plus a sine times a sine, the same two different things inside. And it is very unlikely that you have this in your brain right now, but it is something that at some point when you took trigonometry you came across. It's it's a lesser known trig identity. I'm going to skip the explanation of where it comes from. You may or may not have seen it before when you took trig or in some other context. I'll skip that, but it's sort of it's a like I say, a lesser known but still pretty common trig identity that says that this plus this is equal to cosine, a single cosine of, and then you just do the difference between these two. So theta minus delta. It doesn't matter which one you put first or which one you put second. I could do delta minus theta as well. Cosine is an even function, so it doesn't matter. So we have turned a cosine and a sine separately in two different terms into a single cosine term, and we just had to pay the price for simplifying that part of it with a little bit more complicated on the inside and a little bit more complicated number on the outside. But the benefit again is that it's now down to one cosine. So this is a nice little trig fact that we can turn things that look like this into things that look like this. And this guy we could just call that C, right? C cosine theta minus delta, where the C is equal to the square root of a squared plus b squared. And remember, the delta also is in terms of a and b over here. So it's two new things, C and delta, that are actually, we can trace them back to a and b. Okay, so I can apply that here and turn this into, so what I have in parentheses can be turned into a C and then simply a cosine of, and now playing the role of theta in this expression was beta t, so beta t minus delta. Now I also have the exponential in here as well. So through some trigonometric chicanery, we've turned this into a single cosine. Now, the only reason I'm doing that is because I think this is a little bit easier to think about and understand what it's doing. Of course, we know how cosine works. Let's just talk about cosine itself, right? Cosine itself does that kind of a thing. On the other side it does as well. So what I just drew there is just cosine of t, right? Multiplying by beta is basically a horizontal, depending on whether beta is bigger or smaller than 1. Beta is going to just make it either oscillate more often or less often. So let me draw it as if it's oscillating more often, say. That would be if beta were bigger than 1. So it's just going to be doing it more ups and downs in the same amount of time. And then the minus delta, that just shifts everything. That just shifts everything to the left or to the right. So that would be, maybe it starts here now. Okay, and my picture's getting terrible as I do this on the mouse for the screen. But yeah, so now if I sort of redraw my picture from the very beginning, yeah, it's going to be a cosine that oscillates at some frequency that's based on the beta, and which has a sort of a, it's like where it starts in its up-down cycle is based on the delta. So I get something that kind of goes like just what I drew in red, but now I can see it a little bit clearer. Okay, so that's this part. Now, multiplying by c, of course, will just make it, like if c is bigger than 1, it'll just stretch it up and down. That will just make this go up higher and lower, etc. So that's controlling the amplitude. But now we have to talk about the exponential. Now, let's assume this is a positive exponential. So we have this behavior for the c and the cosine, and now we're multiplying that all by a thing that's growing exponentially. So what will happen there is, and I think I need a fresh page. Here's that growing exponential. And that is what we're multiplying that up-down trig function by. So now the function is going to kind of go like this. So it's an oscillatory behavior. It's going up and down like a cosine, but the amplitude itself is growing exponentially as we go. And so this red thing is sort of the final behavior of our solution. That's what we expect to see. Now that's if it's a positive exponential. If it's a negative exponential, then we're going to have the amplitude controlled by a decaying exponential, right? So then it's going to be something that kind of goes like this. And so it's, again, oscillating up and down, but dying out as it does that. So these are the two possible behaviors. Okay, so let me see if I can get the graphing app to show us something like that. Yeah, okay, there you go. So 2e to the 1/3 t, a positive exponential, and then times a cosine, and we have a beta of 4 and a delta of well, the delta would be positive 0.3 because the negative was built in. And you see the up-down behavior, but growing as time goes on. If I were to change that to a negative exponential, oh, I have to change the scale, hold on. Or maybe what I'll do is I'll change the, yeah, let's make it like that. Okay, so you see it big, and then it's getting smaller. So that's this one. Okay, so you get the idea. And I don't know, maybe just to prove the point, that change to the single cosine is was correct. Let me put in a formula that looks more like our original form. Okay. So let's do like 4 e to the negative 1/3 t. Let's do cosine of 5t. And then let's say like plus 7 e to the, again, same, that's always supposed to be the same exponential times sine, and it's supposed to be the same thing inside the trig function. Yeah, so you see, similar thing. It's going up and down, up and down. Now in this case, the capital C would be, right, here's our A, here's our B, and so 4 and 7, so the C would be the square root of 4 squared plus 7 squared. So 49 and 16, 65, square root of 65. So sort of the initial amplitude is square root of 65, but then the exponential is making it get smaller and smaller and smaller. Okay, so these are what the behaviors of our various solutions to this differential equation look like.